On October 9, 2022, the most powerful explosion observed in human history struck our planet. Scientists are calling it a once-in-10,000-year event. It was so intense that lightning detectors in India went haywire. Germany's instruments picked up disturbances to Earth's ionosphere that lasted for hours. The source? A gamma-ray burst from a dying star 2 billion light-years away. Now here's what keeps astronomers awake at night. If that same burst had occurred just 1,000 light-years away, about 1% of that distance, you wouldn't be watching this video, because you wouldn't exist. Our story begins in the late 1960s. At the height of the Cold War, American military satellites designed to detect Soviet nuclear tests started picking up something unexpected. Flashes, intense bursts of gamma radiation, but they weren't coming from Earth, they were coming from space. The military kept it secret for decades. They couldn't explain it, and what you can't explain, you classify. It wasn't until 1997, 30 years later, that astronomers finally solved the mystery. Italian satellite Beppo Sachs detected a gamma-ray burst and for the first time pinpointed its location. When astronomers calculated the distance, they were stunned. 6 billion light-years from Earth. This wasn't some nearby star. This was happening in an unimaginably distant galaxy. And when they calculated the energy, the sheer incomprehensible power required to be visible from that distance, they realized something horrifying. These weren't just explosions, these were the most powerful events in the universe since the Big Bang itself. A single gamma-ray burst releases more energy in 10 seconds than the sun will produce in its entire 10 billion year lifetime. Think about that. 10 seconds, 10 billion years of solar energy concentrated into two narrow beams of pure destruction traveling at the speed of light. And here's the terrifying part. Because the energy is focused into these narrow beams like a cosmic lighthouse, most gamma-ray bursts miss us entirely. We never even see them. But when one is pointed directly at Earth, everything changes. In 2004, astrophysicist Adrian Mellett published a paper that changed everything. He asked a simple question: could a gamma-ray burst have caused one of Earth's mass extinctions? The math was disturbing. A gamma-ray burst within 10,000 light-years of Earth, just 10% of our galaxy's diameter, would be deadly. The beam would slam into our atmosphere with the energy of millions of nuclear weapons. Within minutes, it would shred the ozone layer. Gone. Just without that protective shield, ultraviolet radiation from the sun would flood the surface, plants would die, the food chain would collapse, DNA damage would spike catastrophically, and it would take a decade for the ozone layer to recover. A decade of our planet being sterilized by its own star. But here's where it gets even darker. Mellett and his team calculated the odds, the probability that a gamma-ray burst has hit Earth in the past 500 million years. 50%, 50-50 chance, a coin flip. Over the past 4 billion years since life first appeared on Earth, the odds rise to 90%. Which brings us to the Ordovician extinction. 440 million years ago, 60% of all marine life vanished in one of Earth's 5 great mass extinctions. For decades, scientists couldn't explain it. No asteroid impact, no supervolcano, no obvious cause. Until Mellott's team looked up, the evidence fits. A gamma-ray burst from thousands of light-years away. Too distant to leave radioactive isotopes we could detect today, but close enough to kill. The pattern matches. Shallow water species survived. Deep water species died in massive numbers, exactly what you'd expect from increased ultraviolet radiation penetrating the ocean. A gamma-ray burst didn't just threaten to cause a mass extinction.
It probably already has.
And it will happen again. October 9th, 2022, 0313 UTC. NASA's Fermi Gamma-Ray Space Telescope saturates. The detectors are overwhelmed. The burst is so bright, so powerful, that it blinds our most sensitive instruments. For 800 seconds, gamma rays slam into Earth's atmosphere. The ionosphere, a layer of electrified particles 60 to 1,000 kilometers above the surface, convulses. Lightning detectors in India trigger. They think they're seeing atmospheric electrical discharges, but it's not lightning, it's 2 billion light-years reaching out and touching our planet. The China Seismo-Electromagnetic Satellite happens to be in the right place at the right time. It measures a massive spike in the electric field of the ionosphere. Scientists had predicted this would happen, but they'd never actually observed it before. Dr. Mirko Piersanti, University of L'Aquila. It changed the dynamics of the whole system. Effects were expected down below but had not been seen at high altitude. NASA called it GRB 221009A. the brightest gamma-ray burst ever recorded in human history, 10 times more powerful than the second brightest on record. Statistically, an event this strong only hits Earth once every 10,000 years. From 2 billion light-years away, it disturbed our planet's atmosphere for hours. Now imagine if it had been 1,000 light-years away. 2 million times closer. The ozone layer would be annihilated. Half the planet facing the burst would be sterilized instantly. The other half would face years of deadly UV radiation. Crops would fail. Ecosystems would collapse. Civilization as we know it would end. And we would have had zero warning. Because gamma-ray bursts travel at the speed of light. You don't see them coming. The beam arrives the same instant as the information that it exists. So the question becomes, are we safe? The answer is complicated. A gamma-ray burst needs to be within 10,000 light-years to be deadly. That's 10% of the Milky Way's diameter. Our galaxy is 100,000 light-years across. The vast majority of space is safe. Gamma-ray bursts are rare, maybe one per galaxy every 10,000 to 100,000 years. And remember, the energy is beamed, two narrow jets shooting in opposite directions. The odds that one happens nearby and points directly at Earth are astronomically small. But astronomically small is not zero. Right now, in our galaxy, there are massive stars in their final stages of life. When they collapse, some will form black holes, some will generate gamma-ray bursts. We don't know which ones, we can't predict when, and even if we could,
there's nothing we could do.
A neutron star collision happens in the Milky Way about once every 10,000 years. Hypernova events, the deaths of the most massive stars, are rarer still. But over millions of years, tens of millions, hundreds of millions, the odds start to stack up. We think it happened 440 million years ago, 60% of marine life gone. When will it happen again? Here's what we know. Gamma-ray bursts are real. They're the most powerful explosions in the universe. One hit Earth in October 2022, and it came from 2 billion light-years away. If a similar burst occurred just 1,000 light-years from Earth, it could trigger a mass extinction event. And statistically, there's a 50% chance it's already happened in Earth's history. The universe is vast. It's beautiful. It's full of wonders beyond imagination.
But it's also violent, chaotic, and utterly indifferent to whether we live or die.
We've been lucky so far. The cosmic lottery hasn't called our number. But every day, somewhere in the universe, a star dies, and two beams of annihilation shoot out into the cosmos. One day, one of those beams might have our name on it, and we'll never see it coming. This video is based on peer-reviewed scientific research from NASA, the European Space Agency, and leading astrophysicists including Dr. Adrian Mellett, Dr. Mirko Piersanti, and Dr. Laura Hayes. All sources are linked in the description below. If you found this terrifying yet fascinating, hit that like button and subscribe for more deep dives into cosmic threats and space mysteries. What scares you more? Gamma-ray bursts, asteroid impacts, or solar storms? Let me know in the comments. Thanks for watching, and remember, keep looking up, but maybe don't stare too long.